Next speaker is Joris Raeymaekers, also from Prague. He's going to tell us about the index for superconformal quiver mechanics.
Thanks to the organizers for inviting me. And it's a nice workshop. It's nice to have a chance to visit Brno. I feel like I don't do that often. The first slide I put was actually meant for a conference in India, but I felt that there is maybe enough Indian people in the audience to leave it on. So 25 years ago, there was the Strings conference in Bombay, and there was exciting time in physics. But there was also at that time shooting going on for a movie called Yeti Jalwa, which means something like it's magic or something like that. And so me and Frederick Denef happened to be asked to be extras. So there's one scene where you see Frederick Denef together with Salman Khan, who's a well-known action hero in the cinema. So Frederick at that time started working on the stuff that I'm going to use very much in this talk, so we will play also a big role in this talk. Okay, onwards. So it's based on mostly on work in progress with very good students of mine, Paolo Rossi, who's finishing his PhD this year, and Andrea Marco, with another very good student, Mustafa Mullah Sanoglu in Istanbul, and in Senghor, also in Istanbul. And we've been working on it for quite a long time, but we spent, I should say, a lot of time on preparing the way and getting distracted with technical issues, and only recently we started to get into the physics. So I'm not going to talk about all these previous papers a lot. So some motivation is, so there are in supergravity solutions that represent multi-degree systems that can sort of disappear down in areas to some kind of scaling limit. So these are interesting because they seem to be, they look very much like black holes. They seem to be, they might be related to black hole microstates. They might give you a handle on areas to CFT1, where I mean really pure areas to CFT1, not like a JT gravities near areas to CFT1. Here I'm really talking about the zeroth order in JT gravity, or in Ashok's picture, like the collection of states that you would say is dual to ADS-T background. And so I'm gonna talk about a certain microscopic description coming from string theory, which is called quiver quantum mechanics. And for these ADS-2 solutions, the quantum mechanics becomes quite subtle. So there's this phenomenon of states which seems to which you can see in a certain limit of the theory in the Higgs branch, but then when you go to the Coulomb branch, they seem to be no longer there. These are called pure Higgs states. Recently, there's been a lot of work on fortuitous and monotone states. The fortuitous states being related to black hole microstates. It might be interesting to revisit these quiver quantum mechanics phenomena in these new ideas, even though I will talk about that. Conceptually, it's also important for the fuzzball picture. So these pure Higgs states are believed to be black hole microstates. If you cannot see them, once you get closer to the supergravity regime, what does it mean for the fuzzball picture? So I'm going to focus on one aspect, which is that you have in this scaling limit and emergent superconformal invariance in this quiver quantum mechanical description. There's an index you can write down, which should give you some new data on this regime. So I will be talking about our computation of this index using localization and its interpretation, which we're starting to figure out. So the outline is that I will start with some review of these supergravity degrade solutions and quiver quantum mechanics. We'll talk about ADS-2 limits and these pure Higgs states, and then I will sketch our computation of the superconformal index with some conclusions. So, deep brain bound states in supergravity. The setting is we look at type 2A, say, compactified on LBR. This donut is supposed to be an LBR. And we can wrap brains of various extensions along the cycles of this LBR, 6 brains, 4 brains, 2 brains, 0 brains, in such a way that they are point-like in the 3 non-compact spatial directions. So you can label these by charge vector. So there's 2 types of supergravity solutions. So, for example, if you take 2 brains with the same charges, they will be like mutually VPS, and you can put them anywhere that they're kind of marginally bound states. Move them apart without energy cost, but there's also proper bound states where you really have to apply some energy if you would like to separate the D brains. And that happens when roughly one brain is magnetic and the other brain is electric, roughly one of them. Whether that's the case or not is measured by this Dirac Schwinger inner product, which basically tells you if the brains form a diamond pair. And so those brains form proper bound states with an angular momentum proportional to this inner product, hidden in the electromagnetic fields. And the NEFM base found the back-reacted solutions to these configurations and go to supergravity. Of course, the simplest solution, single-center solution, is a black hole solution, which was known before. For example, you can make the D0 and D4 charge, well-known black hole, supersymmetric with ADS 2 times S2 in the horizon region, with microscopic entropy, which was explained microscopically by Malvasine, Strominger, and Witten, by taking various decoupling limits and using protectiveness of the symmetric index. Really. Besides a single-centered black hole, there are also these multi-centered solutions, and their positions have to satisfy certain constraints, which are called the NEF equations. So they feature these inner products. There's constant here, which is dependent on the moduli, the values of the scalars at infinity, in such a way that if you vary the moduli, solutions to these equations can start or stop existing, and in relation to walls and all these phenomena. As I already said, these multi-centered solutions carry some angular momentum. For example, for 2 centers, you can solve, there's one such equation which you can solve if this combination is negative here, and then the distance between the 2 brains is quantities. Any questions about this so far? So now I wanted to tell you a bit about this quiver quantum mechanics. So quiver quantum mechanics is a microscopic description of bound states of such brains, which comes from string theory. So it comes from looking at the usual quiver gauge theory on the world volumes of these rapid brains, and dimensionally reducing to 0 plus 1. And as usual in these quiver gauge theories, you can write some diagrams which basically specify all the data entered into the theory. The diagram has some nodes. Those correspond to the D-brain centers. And for each node, there is some world volume gauge field that lives on the world volume of the D-brain, appropriate to the gauge root. I will only look at this talker helium theory where each node is just a single brain. Then there are also excitations from string stretching between the brains, which appear as some matter multiplets, and the number of them is indicated by these arrows, which are given again by this charge and products. And so this theory has two kind of regimes. There is a regime where the brains sort of are on top of each other, and you can integrate out the vector multiplets degrees of freedom, and that's called the Higgs branch. And there is a regime where the brains are separated. Then the matter multiplets get a mass and can be integrated out. It's called Coulomb branch. And which branch is the most is the appropriate one? It's valid one. The valid one depends on the spring coupling. So you have this. Then I have this picture of VPS state metamorphosis, how they sort of morph into each other in different regimes. So here you have the, say, MSW microscopic description. Here you have the Higgs branch, here the Coulomb branch, and here is gravity. Each regime is valid for some values of coupling. There are subtleties with this picture that I come back to later. So we are gonna talk only about the Coulomb branch, and so let me just give you such a crash course on what that entails. So it's a quantum mechanics. It has some fields. All fields depend only on time. Bosonic fields are just the positions of the d-branes in the three-dimensional non-compact space, and there are these auxiliary fields, one for each center. And there are also for each center for fermionic partners, which I label with two doublet indices. Later I will explain that there are two SU2s in the game, so they're transformed under two SU2s in the theory. So to give you an idea of the Lagrangian, it consists of two terms. One is a supersymmetric completion of a term with only one time derivative, and the other one is a completion of a term with two time derivatives. For us, pretty much only the first term will be important, and that term encodes basically the electromagnetic interactions between the brains. So they feel each other's Coulomb potentials, which is expressed in these functions U here, just the Coulomb potentials. They feel each other's Dirac monopole vector potentials. These are these A's here. Fermionic term. And so the second second time derivative part depends on some effective metric on the space of d-brain positions. We don't need the specific form, but there's a first reference one rather than third, and not that small. And also the center of mass degree of freedom really decouples, and I will only talk about relative position of the d-brain. So yeah, worst material. So this Coulomb branch knows a lot about supergravity. For example, if you look at the space of classical supersymmetric configurations, those are ones for which this D field is zero, and with the equation of motion, you obtain precisely the matched equations in the supergravity description. There's another chart for angular momentum, which you can compute, which agrees with supergravity AM angular momentum. And this theory has four supersymmetries, and has also R symmetry, which forms two SU2s. First SU2 is just SU2 of spatial rotations. The second one with this middle is sort of an exotic one, which only acts on the fermion degree of freedom. And the supercharges in the theory are labeled by two doublet indices. So they're doublet in the first and doublet in the second. true. We'll obey the usual supersymmetry. So now I'm going to, if there's no question about this part so far, I'm going to move towards the scaling solutions, and here's ADS2. So I'm returning now to the supergravity picture for a while. So you could imagine a case where these inner products satisfy triangle qualities. Means that they could each be the side of a triangle, and then you can construct solutions to these Dirac equations by saying that the distance between the branes is proportional to these inner products multiplied by some small constant epsilon. So in the Dirac equations, you would get a lot of terms which are basically going like 1 over epsilon, but they cancel out, and the order 1 part can be adjusted to solve the totally constant term here. And in this way, you can construct a solution independent of these moduli parameters f. And you can take this epsilon as small as you want, and as you do that, these D-brane centers move down a deep ADS2 throat. Also, if you do that, when you do that, the angular momentum goes to 0, as was the case for a single center black hole. So these configurations look more and more like single center black holes. So now when you look at this type, this scaling regime in the quiver quantum mechanics, there is a kind of strange phenomenon. So that picture I showed earlier of VPS states morphing into each other as you go from one branch to the other is there suddenly not valid anymore. So there are some states that you find in the X branch description, which you don't see in the Coulomb branch description anymore. These have vanishing angular momentum and also turn out to be very numerous, in the X branch. And so these pure Higgs states are usually interpreted as the states really describing single center black hole microstates. Right. So that raises the question: why are they not visible in the Coulomb branch? One thing should be said is that the analysis of the Coulomb branch is quite subtle in the scaling regime because, as I said, that these braids can come closer and closer together, and that kind of opens up a new kind of a non-compact direction in the moduli space, which makes computations that rely on the homology of moduli space, etc., much more subtle because now it's a non-compact space. I will now argue that this is also very closely related to the emergence of superconformal symmetry, and that is what we propose to use to get a different perspective on the problem. So let me describe how that comes about. Yeah, so when you take the deep scaling limit, where you take this epsilon parameter to be very small, you scale the time coordinate a certain way, you take epsilon to 0, conformal symmetry emerges. So this is a conformal algebra. You can see it emerging in the supergravity side, simply because the supergravity solution becomes asymptotically ADS3 and has this as isometry algebra. So in the limits, so there's some harmonic functions in your supergravity solution. And in this limit, their constant term vanishes, and we have something that For large radius looks like ADS2, but then still has some structure at the brain positions.
So yeah. Should we think about the steep scaling limit as some sort of non-relativistic limit, or no?
I don't,
because
because
relatively scaling time and space
yeah,
in a singular way.
Yes, I don't see a direct. I mean, it could be, but
I mean, it looks very much like it, no?
I'm not sure how it would. Yeah, I mean, yes, I'm already using kind of non-relativistic quantum mechanics. So even before I take the limit, my system is already non-relativistic.
Okay.
But I mean, there might be a way.
Yeah, okay.
So you would say maybe the fluctuations in relativity maybe just could be otherwise. So the conformal symmetry also emerges in a bit more abstract way in this quiver quantum mechanics. So if you take the same limit there, in your Coulomb potentials, the constant term drops out. That has a nice scaling dimension. The same with the symmetric. Has a killing vector, etc. So we can show that this becomes conformal quantum mechanics as the Hamiltonian dilatation operator and special conformal generator, which takes this form, which we'll see later. Also, there is n equal 4 supersymmetry, so the conformal symmetry must combine with that to form some superconformal algebra. And if you look at the classification of conformal algebras with these particular R symmetries, there is a whole one-parameter family of them called D21 alpha, where alpha is a continuous parameter. So the first thing we did in this subject was to determine what is the value of alpha, and it turns out that the alpha is 0, and that's a very special case where the algebra is it's not semi-simple; it's a semi-direct sum in the sense that this second SU2 does not appear anywhere on the right-hand side of your commutation relations, which would not be the case for other values. Anyway, the superconformal charges you can compute from these Lagrangians that I showed you. Again, labeled by two doublet indices under the two SU2 R symmetries, and labeled by plus or minus 1/2 index, which is the 0 weight, and this is a part of the superconformal algebra that they obey. From this anti-commutator, you can derive zeros on unitarity bound, and so you get short multiplets built on the state where the conformal weight is equal to the spin under the angular momentum as you do spin. In fact, since this second SU2 does not appear on the right-hand side, the kind of chiral primary states always come in a full SU2 tilde multiplet, and all these states are annihilated by lowering operators, but also two of the raising operators. And as usual, you can write down an index that basically gets contributions only from these short multiplets and contains information about those, which is usually computable also. So that's our goal here. So let me say a bit more about that. Questions. Maybe first I should say what you do to write a more standard witten index. So there you would pick one of the standard n equal 4 supercharges, say Q minus. So this chart will basically pairs when states like non-zero energy. For every state, you will get another state by acting Q with the same energy and with opposite fermion number, and you can write the standard Witten index. You can do a bit more because this chart has commutes with the total Z component of the let's say the Z component of the diagonal as you do. And so that means you can write, you can keep track of that quantum number by writing refined Witten index this form. In this quiver theory, so Ashok and collaborators also studied an index which was not is very closely related. This one would be called protected spin character. What they studied was something where you do not refine with the second SU2 generator here. So that is in itself would not be an index. So you would first restrict by hand to ground states and then refine those states, keep track only of JHV in those states. But for the specific case of this quiver quantum mechanics, the spectrum is such that the quantity they considered has been argued to be also an index. And it's not exactly the same as what we're considering, but it's very close. So moving on to the superconformal case, the idea is totally the same. So you pick, instead of supercharge, you pick a superconformal or conformal supercharge. Say again, we take G minus plus minus 1/2. You can see that it commutes with some R-symmetry generator, and you can write down a refined superconformal index this type. So why is it useful to do this in systems with conformal symmetry? The reason is that the Hamiltonian, standard Hamiltonian, has their continuous spectrum, so which makes it very subtle to count ground states in a theory, which has a continuous spectrum going down to 0. Trying to pick out normalizable states which sit at the bottom of the continuum is a very subtle problem. While the thing that plays the role of Hamiltonian in the superconformal index is L0 plus J3, and that has discrete spectrum, so that should be a more well-defined object in the conformal systems. Now that I told you about quantum numbers, etc., I can tell you a bit more about this pure Higgs states. They also have special R charges. So first of all, the states you do see in the Coulomb branch are of the type that they have non-vanishing angular momentum as you do spin, but they have vanishing spin under the second as you do. And as I explained, these are interpreted as kind of multi-center deep red bound states. While these pure Higgs states that I mentioned before, they have actually vanishing angular momentum, which makes them candidates for single center black hole microspace. Black hole also didn't have any angular momentum, but they in general have non-trivial spin under this second SU2. And if you look at the contribution to this superconformal index, the Coulomb-like states contribute quite differently from the pure Higgs states. The pure Higgs states contribute a full SU2 twiddle character. In particular, pure Higgs-like states, they contribute whole terms and constant terms to the superconformal index, while the Coulomb states just contribute positive powers of 3. So this would be at least some kind of diagnostic to see if you're capturing pure Higgs-like states with your superconformal index. To see if you have poles There is a caveat in what I told you so far. I mean, all the limits I took were all well defined, nothing blew up and stuff, but we also made an approximation to begin with. That's where the caveat comes from. So we had integrated to go to the Coulomb branch, we have integrated out some matter molecules whose mass goes like the separation between the branes. So when the branes become very close, those states become light, and the effective description becomes questionable. In particular, there are further corrections which we have neglected, which come from superpotential in the Higgs branch. So those don't couple that the superpotential don't couple directly to the Coulomb branch fields, but it would enter at two loops, and that would give corrections which actually break superconformal symmetry. I talked about no one has really computed them. From dimensional analysis, it could give some correction to the metric of this type, for example, which would actually be very strong in the regime that we are considering. I mean, we become very strong when the branes get close together. It's kind of interesting to know that this would be compatible with another superconformal algebra. That's just speculation. But so suffice to say that there are strong corrections when the d-brane positions get close together, where the Coulomb branch should kind of merge in the Higgs branch, and our description breaks down. That we should keep in mind. So now I will, there's questions, move to the computation. So I'm going to close my eyes and look through this caveat, compute the thing, and then see if we can interpret the results.
The goal is to get the pure Higgs states from the Coulomb branch.
Well, that was our that was our initial goal, or to see if they are there. If we see them in the superconformal index. Yeah. Well, we will see some of them. We will see some approximation to it exactly. We will not get all of them. So yes, there are two things. There are two things you need to know to do this index computation. The first thing is that the supercharge we picked to define our superconformal index is related to the one we picked to define the Witten index by some similarity transformation with a special conformal generator. And if you work it out a bit, you can see that this similarity transformation you can alternatively describe as you can absorb it in a redefinition of your Coulomb potential and vector potential background fields. So we shift them as follows. And in this way, the superconformal index formally to compute it is the same as computing the Witten index, just in a modified electromagnetic background. So we can do the two at the same time. The second observation comes from writing a path integral for the index. So this was the one that we started with. You want to treat this as this whole thing as a Hamiltonian, and then the genre transformers you get from Lagrangian, which now depends on theta is the fugacity. It's slow to this refining parameter, chemical potential as well. And again, this Lagrangian consists of a first order and second order part. And the main thing we will use is that the first order part is almost completely supersymmetry exact. The thing that remains is that component of the angular momentum and some other terms which anyway will vanish in the end. So as usual in supersymmetric localization, you can take this exact part and you can multiply it with some parameter lambda. and nothing will depend on that lambda. Then you take lambda to infinity, then you see that the path integral has to localize, first of all, configurations where the velocities are zero, so the constant configurations. Also, this term cannot be there, so localizes on the fixed points of the killing vector, which generates rotations on the z-axis. So it basically localizes on T-brane positions, which are all on the z-axis. And then you still have this auxiliary field here, which basically gives you some kind of delta function. And if you integrate over 0 point, you get delta function on the zero values of these shifted Coulomb potentials. The thing that you would call in ordinary supersymmetric case the classical mobilized space. Sense? Yeah. Okay. So if you do this, you get some fixed point formula for the index. The formula is the same for the Witten index as for this index. It involves, yes, it's a sum over fixed points of certain equations of q to the power classical angular momentum. And there's a factor from the one loop determinants here. So if you want to compute the Witten index, you have to find the solutions on the z-axis of the F equations. This form, this agrees with the way Schoch and Mansfield and Fielding wrote their index. And the way we derived it here is a bit similar to what these authors did. So that's kind of a check that it gives for the Witten index, the known result. And for the superconformal index, you have to localize on a different T-brane configurations on the z-axis, which have to satisfy these equations now, which involve here this kind of part from the superconformal given by this special conformal charge. So if you work it out, here are some examples for a G-center case. So what I want to say is that our superconformal index does have poles, so it does seem to have contributions from these pure Higgs-like states. On the other hand, I mean, on the other hand, it doesn't capture all of them, not nearly. So you could look at the exact microscopic result for the Witten index, and you find that it has the same powers, but there's many, many more states that you can see here. So what's going on? What does this mean? So there is a way to see what we found. Our formula as a first approximation to an exact formula written by Violin et al. So to see it, we can write our localization equations as extremizing certain potential. They have the exact result, which also extremizes certain potential, which looks like this. Then you can say, like, our approximation is supposed to be valid only when the branes are sufficiently separated from each other. When these z's are much bigger, the z's here are much bigger than the second terms. And you can make an expansion, and you notice that the first term in this expansion is precisely the one we found here from the superconformal index, up to some prefactor which you can rescale without affecting the contribution to the index. So it seems like our superconformal index doesn't give you everything, but it gives a first term in an infinite series associated with the exact result. Then I was going to talk about some generalizations, reformulation of this, but maybe I'll skip that until the time. So the conclusions, I mean, the physical picture of what we've done is not yet crystal clear. I think we have a handle on the computational part. But it does seem that through this superconformal index, the Coulomb branch knows a little bit more about single center microstate than previously thought. Something I would really like to know is what these infinite further corrections in the exact formula mean from the point of view of the Coulomb branch. Can we just give a physical interpretation of them in terms of stuff we have neglected in our approximations? Can we derive them or we great? Another interesting question is what the superconformal index would look like if you try to compute it in supergravity. So people have made a lot of progress, for example, these authors, on computing indices in supergravity and finding specific configurations which contribute to it. So it would be interesting to see if these equations we got here are a bit like modified the Neff equations, if they come from some supergravity analysis or some modified version of them. Something else which is not really related to what I said here today, but I think would be interesting to try to see if there's a link between this pure Higgs versus Coulomb states and the recent work on fortuitous versus monotone states, which I think in some more supersymmetric cases has been explored, but they're not published. But for the models I talked about, it's not yet done. Yeah, I'll stop there.
Do you have any questions to this? I'm fine. So now we have a 15-minute break, and then we'll continue with the last two talks. Thank you, Ursula.